Good afternoon. Okay, thank you, folks. This is the last session of the Using Docker track, and it's a doozy. Do people still say it's a doozy? It's a thing from the 1950s. We've got two fantastic speakers. We've got Nico from Docker, and we've got Karthik from Tigera. Tigera make Calico, which is a Kubernetes networking implementation, which we use in Docker EE. And this session is going to be all about teaching you how that networking stuff works. So big hand, please, for Nico and Karthik.
Good afternoon, everyone. My name is Nico, and I'm at Docker. I'm a solution architect at Docker. And with me is Karthik from Tigera. We've been working together with customers basically day in, day out on designing and implementing Kubernetes networking. And today, we're going to be talking about that implementation. So let's start it out with the poll. Hopefully you're still with me, and I'm like keeping away from a drink. Who is designing a Kubernetes container platform? Raise of hand. That's right.
Yeah, I think we should probably ask who's not designing a Kubernetes cluster. I think looks like everyone is.
Yeah. So if you are, who is intimidated by Kubernetes networking? The same folks.
By the way, we're going to do that same poll at the end of the session.
Yes.
And if you're not, you're staying behind. We're getting drinks in here.
Yes.
You're having a party. You're not leaving this room until you're not.
So folks, this session is for you. If you are designing a Kubernetes-based platform and you are somehow intimidated by Kubernetes networking, it's okay. We are here to go through, start out with kind of the basics of Kubernetes networking and Calico. We're going to talk about the integration of Calico into the Docker platform, see how that architecture looks like. We're going to walk you some design considerations to think about as you're designing and implementing a Kubernetes-based platform using the Docker platform. And we're going to do some demos, of course, through an application deployment towards the end. We'll wrap it up with key takeaways and Q&A towards the end. We know we might go a bit over time because Kubernetes, networking is, sometimes we're going to slow down, make sure that everyone kind of is with us. So we'll probably go a bit over time, and we'll be hanging out towards the end of the talk to answer your questions. So with that, as we work with customers day in, day out, we feel that we see that there are three key design considerations when it comes to starting off designing a Kubernetes-based platform. You're probably dealing with, the first one is you're probably dealing with not a greenfield kind of all new infrastructure that is very homogeneous. So you're dealing with a very diverse set of infrastructure, your own data centers on-prem, different sets of hardware, different operating systems, different network layouts, different fabrics, and so on. Or if you have if you're already using the public cloud, or you're purely on the public cloud, also each public cloud has its own nuances when it comes to that network infrastructure. So the first key thing around the building a enterprise platform, Kubernetes platform, is to make sure that you're building something that can go beyond what you currently have. You're building something for the future that takes into consideration the complexity of such diverse infrastructure. The second key consideration is around the applications that you're onboarding into the platform, right? So you're going to be dealing with monolithic applications, legacy applications that you're containerizing and you're putting on the platform. And you're also going to be dealing with microservice-based applications, both Windows and Linux-based applications. So it's really important to not only just think about the infrastructure, but also to think about the applications and profile and the portfolio of the applications when you're designing platform, to truly understand what the application requires from the network when it lands on that platform. Finally, it's really important to build a zero trust security model around that platform. Today's applications and today's kind of security risks, in fact, require you to think that way, to build something, to build the security model as close as possible to the application. Building something that's based on primitive kind of firewall, kind of legacy primitive is not that's not something that works in today's world. So just remember those three considerations. I'm going to walk you through each, as we deploy the application down the road. But before we get there, I want to make sure that we start with the basics. So Karthik, how about you walk us with Kubernetes connectivity basics?
Sounds good. Thanks, Nico. And yeah, so specifically, we use the term connectivity because connectivity leverages so many more things beyond just the networking, right? There's security, there's other elements of connectivity. So for those of you who raised your hand when you said you were intimidated, just stick with us for the next 10 minutes as we cover these sort of concepts which are really core to the common abstractions that people use for connecting applications together in Kubernetes, right? And once you understand this, everything will fall into place and you go like, this is so intuitive. To begin with, when the unit of deployment in Kubernetes is a pod. Hopefully you guys know that. A pod is a collection of containers. And pods in Kubernetes, every pod has an IP address. And Kubernetes is spinning these pods up and down dynamically based on what you specify ask Kubernetes to do or based on its auto-scaling setup. And these pods need to be connected. Kubernetes uses an abstraction called CNI, the Container Network Interface, to get these pods to talk to each other over the network. But because pods are dynamic and transient, you need a way to talk to a service or an application even as Kubernetes is spinning up these pods dynamically. And the abstraction for that is it's called services, typically implemented by something called kubeproxy. So you can talk to the service, and the service endpoint is well-defined and fixed, even as in the back end, Kubernetes is dynamically spinning up pods. So that's the second concept we'll explore. The third element is something called network policy, because now, as Kubernetes is dynamically spinning up pods, each pod comes up with a distinct IP address. So when you look at things like firewalling, microsegmentation, policy rules, you can no longer rely on things being fixed. And especially as you move to cloud-native architectures, things are much more transient. And so Kubernetes provides this nice abstraction called network policy that the team at Tagara helped define in Kubernetes, working with the network community. And this allows you to have a higher level abstraction using labels, which we'll explore, so that this is giving you dynamic microsegmentation. Fourthly, when you refer to things like services in Kubernetes, you'd like to be able to refer to them by name. And so kubedns provides a dynamic name to IP translation, and so you can use domain names. And finally, ingress is a concept that is typically used when you're connecting to applications from outside the cluster. And when you expose things to an ingress resource in Kubernetes, you get a well-defined DNS name typically, and things like SSL termination. So from outside coming into the cluster to access an application, you typically can do things like do SSL termination, look at the HTTP headers, and redirect based on what the application is trying to access. So that's the fifth concept. And we'll sort of go through each of those in turn. Let's start by first looking at a nice, new, fresh Kubernetes cluster. You haven't scheduled any pods yet. Typically, you provide the API server in Kubernetes with an application to deploy. And the application is going to consist of some container images that you're going to deploy as pods. And you're going to tell Kubernetes, hey, deploy this application with a certain number of replicas. And so Kubernetes will schedule those pods on different nodes and talk to this agent called kubelet, which is running on the given node. And tell the kubelet, hey, can you schedule this pod with this container and get it connected, right? So what kubelet does is it creates this pod, and a pod essentially is a collection of containers with a shared network namespace. So everything within the pod is in a different network namespace from the host. I'm going to assume you guys all know what a namespace is. And then the next thing the pod does is it calls out to the CNI plugin. So we're going to be using the Calico CNI plugin in this example. And essentially, the kubelet will tell the CNI plugin, hey, I have this pod here in this network namespace. Get it connected to the rest of the network. And so when it calls out to the Calico CNI plugin using configuration that's stored in /etc, the Calico CNI plugin says, great, I have a pod with a virtual Ethernet that connects the pod's network namespace to the host's network namespace. I need to get it connected to the network, so first I need to give it an IP address. Every pod has a unique IP address in a Kubernetes cluster. It uses an IPAM module, typically by default that is Calico IPAM, and gives that pod an IP address from a pool of IP addresses it manages. and says, okay, I've got this pod now connected to the host. I need to now get it connected to the rest of the network. And so the way it does that is it writes this workload information, the pod's information, into the Calico data store, which happens to be running on something called etcd. etcd is a distributed key value data store that's also used by Kubernetes in the control plane, and something that typically runs on the master node. And so when you write data to one etcd server, it gets replicated to all of the other etcd servers. And once it does that, we have another agent running on the host, typically as a privileged pod, called Calico node, that asks to be notified anytime pods get scheduled on a node. So now that it gets notified by the etcd saying, hey, you have a new pod, what Calico node is, it creates a route in the Linux routing table saying, to get to this pod's IP address, use this virtual Ethernet. Simple IP route, right? And then advertises this route to all the other nodes in the cluster. So literally every other node in the cluster gets this typically an aggregated route for that pod's IP address. And now every node in the cluster knows that this pod happens to be running on this particular node. So from that point onward, pod-to-pod connectivity is IP routing. If you do an IP route show, you'll see routes. And you just, Calico simply creates the routes in the Linux routing table and allows Linux to do the routing, right? So that is pod networking, that's all it is. Simple, scalable, powerful. Now, let's go a little bit beyond pod networking. Now we assume that all of you guys know that all of the pods in the cluster can talk to each other. So every pod has an IP address, every node in the cluster knows how to reach a pod. So that's full connectivity. But the next thing you have to deal with is now pods are transient. So let's say a pod dies. Kubernetes, which is declarative and dynamic, spins up a new pod to replace it. Let's say your performance starts to tail off and we set up horizontal pod auto scaling in Kubernetes. Kubernetes is going to create new pods. So as you do that, let's pretend you're trying to access an application in Kubernetes. You need to have a well-defined abstraction by which to access the app. And that abstraction in Kubernetes is called services. The way this works, typically in Kubernetes, is it uses a function called kubeproxy. And when you expose a deployment as a service in Kubernetes, what Kubernetes does is it gives that service typically a well-defined, typically a IP address, a cluster IP address, which is essentially a virtual IP address. And it then goes to every node in the cluster and sets up IP tables rules, specifically IP tables NAT rules, that says anyone trying to access this cluster virtual IP, translate it to one of the backend pod IP addresses. So essentially it sets up IP tables rules, and it uses a fairly basic load balancing heuristic so that the traffic gets distributed among the different pods. And it's all done with IP tables magic, but it's very simple. And in effect, that is typically the default service that's available, but you also have a couple of other service types. So cluster IP works great when you have things inside the cluster trying to talk to each other, but sometimes you have things from outside the cluster that need to talk to a service. And for that, Kubernetes has a concept called node port, which is a different type of service. And in this case, it assigns a well-known port, typically from a range, in the case of Docker, to be 33,000 to 35,767. And similarly sets up the IP tables rules so that traffic sent to the host's IP address with that port gets translated to the backend pod, or one of the backend pods. Right? So that's the second type of service. And the third type of service is something called a load balancer, where optionally for a certain number of well-known load balancers, Kubernetes also sets up an external set of load balancer rules on that load balancer, such as one of the cloud load balancers, so that it can, an external load balancer can dynamically translate to one of the pod addresses. Right? So those are different kinds of services available in Kubernetes. And all of these are orchestrated by kubeproxy, so when you expose a deployment as a service, these rules get set up on every node in the cluster. So you can try and access a service from any node in the cluster, and it should work. Okay? So that's the second concept you guys should understand. The third concept is when you're trying to access an application from outside the cluster. A commonly used way to do this is something called ingress. And essentially what you do is when you have a deployment in Kubernetes, you can say, I want this to be accessible via an ingress resource. And in that ingress resource, you say, I want anything that is sent to this particular URL to be sent to this service, and then sent to this other URL to be sent to a different service. And typically, you have an ingress controller that fulfills that ingress resource. It could be Nginx. It could be, there's a whole variety of ingress controllers. And what they do is when this resource gets exposed, they say, OK, I'm now going to allow inbound connections from the outside, potentially provide a nice DNS name so that external applications can use a nice DNS name with potentially wildcarding, and terminate the HTTP connection, potentially a TLS or SSL connection, look at the headers, look at the URL, and decide how to redirect it at the back end to the appropriate either service or potentially to the pod directly, right? So this is a nice way to access services from outside the cluster, but typically ingress works for things like HTTP and HTTPS with a select number of other protocols, unlike something like a load balancer, which is typically a layer 3 or 4 construct, right? So this is the third abstraction. And sort of walking to that animation here, essentially from the user tries to access this DNS name pointing to this ingress resource. Essentially, that gets terminated on the ingress controller. It looks at the headers and then redirects it to at the back end to the appropriate set of endpoints or pods. And the fourth concept is network policy. Again, keep in mind, this is a dynamic and declarative world, right? Pods are constantly churning based on load. The value of Kubernetes is you tell it, here's my application, make sure it meets this performance, make sure this is maintained. I want a deployment with 5 pods. And even as individual pods die, Kubernetes automatically spins up new pods. But every pod is a unique IP address. And by default, if you don't do anything else in the cluster, every pod in the cluster can talk to every other pod. It's a wide open environment, which is not something you want. You want to lock it down such that only the things that want to talk to that should be allowed to talk to each other do. And so the way you do that in Kubernetes is, first of all, you have to understand that in Kubernetes, everything can be labeled. You can label pods, you can label deployments to say this is labeled web server, this is labeled Redis server, or role equals Redis server. You can label things to say this is stage equals dev. So you can give an arbitrary set of labels to objects in Kubernetes like deployments or pods. And then with network policy, you can define a set of constructs that say, I want to allow all things labeled role equals web server to talk to all things labeled role equals database server, as long as they have the label staging, as long as they have the label customer A or tenant A. So rather than rely on low-level constructs such as IP addresses for isolation, now you're relying on a higher-level construct like labels. And then it's up to the network policy implementation, in this case Calico, to dynamically create the microsegmentation rules to ensure that only those applications can talk to each other. And essentially, Calico runs a Kubernetes controller, so it keeps track of network policy objects and changes, and dynamically creates these IP tables rules across all of the appropriate pods where those rules need to be in place. So in effect, now you've gotten dynamic rules for isolation of specific applications from each other, independent of Kubernetes churning these up and down. Right? So that's the last concept I want to leave you with. And we'll come back and now reinforce it in a few minutes with an actual application deployment, and to really walk you through how easy and how nicely these concepts can work with each other. To kind of summarize Calico that we at Tigera work on, and this is something that is one of the most popular, not just network plugins, but the network policy implementations for Kubernetes. Focus is on keeping it simple, scalable, and robust. So all of those are key focus for us. Simplicity, you talked about the fact that, again, this works with no overlays being required. This is IP traffic, so when you look at the actual application traffic, it is IP. Being able to troubleshoot IP, any of you in the room hopefully can do it, right? We'll give you some examples of that. But also from a network policy perspective, this is very widely used across the industry. In fact, today, the big 4 cloud providers all use Calico as part of their default hosted Kubernetes platform. So when you get Kubernetes from Amazon on EKS, Azure with AKS, Google with GKE, and IBM Cloud, they all use Calico out of the box. And it doesn't just work on Kubernetes, but it also works on virtual machines and host instances outside of Kubernetes. So you can actually manage a policy across heterogeneous environments. even as Kubernetes is spinning things dynamically, right? So it's a very dynamic and powerful concept that I want to emphasize. Okay. That said, I'm going to hand back to Nico to go into a couple of examples of how Docker pulls this together.
Cool. So we kind of went over the key concepts of Kubernetes networking, we went through the Calico CNI. Now, if we take a step back and see how that actually applies to you as you're building the platform. So I'm not sure how many of you guys have Docker Enterprise Edition or using it. I'm seeing some hands. So just to recap, Docker Enterprise Edition has 3 main components: UCP, DTR, and the worker nodes. Basically, UCP is how you basically manage the Kubernetes cluster. We shipped Kubernetes as part of UCP in April with WinGA. So it's basically how you control and manage an enterprise cluster, and you deploy your containerized applications on it. DTR is the secure registry, so you can keep your images and there's scan images and basically store their images in H8. And the worker nodes are where you actually deploy the application containers or pods. In EE 2.0, which we shipped last April, one of the things that we've done is we kind of added Kubernetes, and we're basically Kubernetes conformant. And we picked Calico as a default CNI in the platform. And what basically from an architectural point of view, we wanted to focus on the simplicity of provisioning everything related to networking. So when you create this cluster out of the box, Calico comes pre-installed, zero-touch provisioning. We configure it for you, make it highly available for you. We deploy it as a daemon set that runs the Calico node process as a pod on daemon set on every node. And it kind of takes care of all the networking and plumbing for pod-to-pod connectivity, as well as the network policy enforcement. So the manager nodes also act as Kubernetes masters. They have all the Kubernetes components that runs on the master, the API service scheduler, and the controller. And the nodes have the kubelet and kubeproxy. And they basically, you layer Calico on top of that, and here you go. You have a very straightforward Kubernetes deployment that you don't actually have to figure anything from a networking perspective. That doesn't mean that you cannot, like if you have advanced configuration, you can directly interact with Calico and Kubernetes if you want to change any of those kind of default configuration there. But out of the box, it works, and it provides pod IP connectivity. And as kind of Karthik went through, the Calico nodes peer with each other, and they basically populate the layer 3 IP routes between the different nodes to the point that you provide a native host networking that basically gets installs the routes, so pods understand exactly what's going on, and they know exactly how to route the traffic to other pods. So let's take a look at, I have this cluster that runs on the public cloud. EE can run on-prem or in the cloud. Let's take a look. I have a sample cluster that we have 3 manager nodes and a bunch of worker nodes. So let's do that. Hopefully the Wi-Fi is working as requested. So this is the main screen that you see in UCP. And you can see that if you go to, let's take a look at the number of nodes here. You can see here I have a hybrid environment. We have Windows and Linux. You can see I have like 13, 14 nodes that are running across different availability zones. Basically Kubernetes is running there. You can interact with UCP out of the box from the UI or the CLI. So if you want to basically let's take a look at the Calico integration here. So under the kube system namespace, which is basically the default namespace for everything related to the kube system components, you can see that out of the box you have Calico node. It runs as a daemon set. And as I said, out of the box it does provision Calico and provides the connectivity. So I can also interact with it from CLI. I can do get nodes. So if you're familiar with the Calo commands, you can just use those, and you can deploy the applications out of the box you get the pod-to-pod connectivity and all the kind of magic that Karthik went through.
By the way, can the guys in the back in the room, can you see the font here? Is it big enough? Good, great.
Good, perfect. So let's go back. This is just an overview of what the platform is. Hopefully that kind of made sense. Out of the box, when you provision it, you get all those components.
Sounds good. And now let's take an actual application, deploy it, and show you how all of the constructs we talked about, how they're actually working in practice, right? So you can go back home and try your own applications on your Docker clusters. So what we have here is, as Nico mentioned, we have a little cluster. We have a cluster that's got a set of Kubernetes master nodes running within, as well as a bunch of worker nodes. We also have a set of ingress nodes as well, where we're running, in this case, the Nginx ingress controller, which Docker nicely packages together. And what we're going to deploy here is an application that consists of 3 services. It's a client service talking to a front-end service, talking to a back-end service, and they're simply talking to each other over REST API calls. And there's a management UI that pulls each of them and gets connectivity and displays a nice little graphical UI of what the connectivity is. So let's go ahead and deploy that application, Nico. So if we go to the cluster, and let's deploy it first, and I'll show you what's in the manifest. So this consists, as you can see, of a number of deployments and then services, right, being created for the individual deployments. So if you look at the individual deployments, so let's start with this one here. So essentially, what you're seeing is first a service being exposed, but that service is being backed by this thing called the Replication Controller, where you said, I want to have one replica of this backend. And notice the thing that says labels role equals backend. We'll come back and we'll use it for the network policy example. Essentially, when you have a deployment in Kubernetes, you can assign it an arbitrary set of labels, essentially key value pairs, which you can then use for other functions in Kubernetes. So just as we have a front-end application pointing to a given container image, you similarly have, like we talked about the backend, now we have a front-end. Same thing, you have a deployment and then a service that is exposing that deployment. Okay, so and now we have other, like a client version as well. So let's start by first looking at the UI to see what, let's, go back.
Yep.
Also notice that the management UI, which is giving the graphical UI, I've exposed as an ingress resource. Specifically, this is how you expose an ingress resource in Kubernetes. Basically, it's saying, I'm going to give it a well-defined host name, and saying anything coming to /, I'm going to redirect at the back end to this management UI service, right? And different ingress controllers can potentially optimize that even further by talking to the pods directly. But let's take a look at the UI of the application we just deployed. If the Wi-Fi cooperates, essentially you have these 3 applications or services talking to each other, and the management UI is showing connectivity. Basically, all of these things are able to talk to each other. And that's the default state in your initial cluster, which is you haven't done any isolation, so everything can talk to each other. But let's take a couple of quick looks. So let's log on to one of the nodes in the cluster and see what the networking looks like, starting with pod networking. So let's pick any random node where there might be some pods running, and if you do an IP route show, let's see what we see.
Sure.
So fair enough. So if you look at the IP routes on this random node here, you notice there's a bunch of /32 routes pointing to this interface called Kali something. Each of those Kali interfaces is a virtual Ethernet pointing to a given pod. So every pod has a /32 route. Every pod running on that node has a /32 route saying to reach this particular IP address, send traffic into that virtual Ethernet. The other thing you'll notice is some /26 routes, if you can highlight that, Nico, pointing to other nodes. Basically, it's saying this is for all the pods running on remote nodes. Here's an aggregate route. So essentially, what Calico has done is it's created routes in the Linux routing table saying to reach the containers or the pods on this host, send traffic to the corresponding virtual Ethernet. And to reach pods on different nodes, send traffic to those remote nodes. At that point forward, it is IP routing, right? So fundamentally, Calico, what it's doing is setting up routes in the Linux routing table and letting Linux route for you. So that's the pod networking to begin with. Now let's look at services. So let's start, we've exposed things like backend and frontend as services. So Nico, if you do a kubectl get service -o wide -n for the stars namespace where we've deployed this application. Notice that when we've exposed each of these services, Kubernetes has given each of them a cluster IP, which is the default service type if you don't specify a specific other kind of service. And so you have each of them that's been given a virtual IP, which is now being plumbed by kubeproxy on every node in the cluster using IP tables NAT rules. So if you go to any node in the cluster and do an IP tables dash capital L, yeah, there we go. And grep, actually you have to change the IP, grep for the cluster IP we just, notice there's your kubeproxy inserted rules in the NAT table that's saying anything coming to this particular IP, translated the backend. And there's a little bit more magic here, but fundamentally the rules itself, once you understand it, are very simple, which is I'm going to take anything coming to this cluster IP and translate it to one of the backend pod IPs for that particular service. So if you actually go back and do other kubectl commands like kubectl distrib, let's not do it now, you will actually see the different pod IPs that compromise that service. In this case, we have a service with just single pod, so you're not going to see much. But if you have a service with 10 pods or 15 pods, you'll see all of those pods in the load balance pool, right? And kubeproxy sets up some basic IP tables NAT heuristics to do some coarse-grained load balancing. We could have gotten more sophisticated and set up external load balancers, such as a cloud load balancer, or set up a node port. But for this introductory talk, we figured we should keep it simple. We already saw the concept of an ingress resource. I'm not going to go and show you more detail on Nginx, but fundamentally it's working. The Nginx ingress is working to terminate connections to the well-defined host name that you've exposed externally and send it at the back end to the service. So that's the third concept. Now, the next thing we will explore that we talked about is network policy. So as you saw from the UI, all three services are able to talk to each other openly, right? Which is maybe not something you want. Maybe you want to say the client should be only allowed to talk to the front end. The front end can only talk to the back end. Leaving wide open environments is typically what causes the big security issues that we hear about every day. So let's do that by applying some network policies. Let's apply it first, and I'll show you what's in the policy. So Nico just applied a security policy with some rules, and let's explore those rules in more detail. So the first portion of that manifest that you see is I'm taking the stars namespace where we deployed the application into, and we are saying default deny. And what that means is we are saying from this point on, none of the pods in that namespace will be allowed to talk to each other. If something needs to talk to each other, you need to go in and explicitly allow it, right? So let's go to the next section of the network policy, which is the backend policy. The first thing, if you can highlight the part where it says match labels, you notice it says match labels role equals backend. What it's saying is this policy needs to apply on anything that has the label role equals backend. And the policy itself is saying the ingress policy, so traffic coming in, filter, and show, if you could highlight, Nico, the from part. Basically saying only inbound traffic that's allowed is from anything labeled front end. And only inbound traffic needs to be on port 6379. So essentially what we have said in that policy is the backend, anything labeled backend will only allow things from things labeled front end on port 6379. Similarly, we go to the front end policy, same kind of concept, except we're now matching on things labeled front end and allowing things labeled client, port 80 to send traffic in. Kubernetes network policy, you can also have egress network policy, you can have CIDRs. Calico extends it with much more advanced concepts and much more advanced expression syntax and works consistently. But fundamentally, network policy is very simple. You use labels, and now it's up to Calico to dynamically create IP tables rules and IP sets for scalability so that it's in a single kernel lookup, you can actually look up who needs to talk to what, right? And it does that in a very dynamic fashion. So now if you go back and look at the UI and hit a reload in the UI, notice that we've locked it down such that the client can only talk to the front end and the front end can talk to the back end. This is just with deployments with one pod. Now imagine in your production Kubernetes cluster, you have dozens or hundreds or thousands or tens of thousands of pods. You absolutely do not want to leave your cluster wide open, and you absolutely want to start using primitives like network policy to dynamically lock down your environment and to be able to automate some of that, which we'll come back and talk to in a little while. So that said, Nico, what do we have next?
Yeah, so thank Karthik. I mean, we just saw that like with Kubernetes out of the box, you get all the pods can communicate with each other, and you basically you have the flexibility with the integration in the platform to start locking down, making sure that only services that need to talk to each other can talk to each other.
Yep.
And everything is label-based. So if we revisit kind of the consideration we talked about earlier, we saw that we deployed, we had the platform that integrates Calico that allows you to basically truly take advantage of the powerful Calico integration without having any on-delay dependency. As long as basically the nodes can have IP reachability, that's all the on-delay requirement. This means that you're not locked into the infrastructure if you're kind of going from older hardware to the newer hardware, or older data center to the newer data center, or you're moving to the public cloud. You actually have that flexibility. That's really key here. Again, simple zero provisioning. You don't need to worry about all the integration here. Docker and Calico are well integrated together for you. And this can run on any infrastructure, any cloud. The second piece that we want to revisit is to truly think around the application portfolio that you have. I'm working with customers who go and build an amazing platform, but then they forget to kind of start thinking about the application early on in the process. It's really important to understand the applications that you're targeting to Dockerize and onboard into the platform, and see, if you're dealing with monolithic applications or legacy applications, what type of network profiles they present here, and model that with what Kubernetes in Docker EE and with Calico can give you. So if you're more focused on pod-to-pod connectivity that comes out of the box with the Calico CNI, you select the right set of service abstraction, and basically how you expose the application, whether you're using cluster IP, node port, externally, or load balancer if you're running on the cloud. If you're exposing any of the applications externally through proper DNS with SSL termination, then you probably need to pick Ingress. DNS comes out of the box with kubedns. And the network policy, we've seen it with our application deployment, how we enforce a policy dynamically using the Calico policy enforcements there.
And yeah, just to actually go back to one last comment I'll make there. And again, like Nico said, I want to emphasize, these are concepts that work well together. You don't need to use all of them. Each of them are very powerful concepts. But we walked through a simple application demo showing you this is very straightforward if you know how it works. Things like network policy, using network policy is very simple. Just you already got labels and you define it. Now, there's a lot, at the beginning of the talk, Nico talked about how you don't want to rely on just perimeter security, right? Now in an environment like Kubernetes where things are dynamic, you have a lot of power where you can isolate different things to sort of talk to each other, and this sort of segues into the concept of zero trust. There's a number of things that you can leverage network policy for, including things like stage and tier separation. You want to separate your dev clusters from your test clusters from your prod clusters. Being able to isolate different tenants from each other. In fact, we have a number of large cloud service providers that use our network policy implementation, including a number of commercial products providing additional RBAC control, additional audit logging, and additional features to not just give policy controls to individual customers or projects, but then to isolate the customers from each other. And since this is all being done at the point in which the pod connects into the host, you don't have to worry about keeping complex network overlays. Your networking itself can be really simple, which is IP traffic being routed by Linux. So when you have to troubleshoot networking, it is IP traffic. And you use this much more powerful network policy language to be able to isolate applications from each other, certainly for the dynamic microsegmentation rules, which Calico extends and provides you more power by taking it not just in Kubernetes, but taking it to virtual machines, taking it to environments outside Kubernetes, and being able to orchestrate all of these workloads in cloud-native environments with additional capabilities around compliance and so on that are built on top of that, right? So really powerful concept, helps you lock down your Kubernetes environment. Please do, as you deploy workloads in Kubernetes, do not please leave it open.
No. Finally, one takeaway from this session. Hopefully this was helpful. We actually are on time. I thought we were going to go over. I guess I didn't.
We're probably going to have some questions. Right?
Yeah, we'll have some questions. But one takeaway. Think about those design considerations that we went through. Think of what you're building and what you're designing, or you're in the process of designing. We showcased how EE platform comes, out of the box with Calico. You can basically skip all the hassle of the provisioning and the high availability and security that comes in the platform, and basically utilize the choice that the platform gives you to run your applications, monolithic or microservice applications, on the platform, on a hardware, on-prem or on the cloud, all while enforcing a dynamic, policy-based microsegmentation to secure your applications anywhere. So with that, thank you very much for being with us and coming to this session. We'll leave it up for questions. Please join the community on Slack, and we actually have a trial if you want to take EE for a spin, trial.docker.com. It comes with everything we showed you is there. So with that, we'll leave it for questions. I think there are some mics.
While folks are going up to the mics, I will echo what Nico just said. When you try out your Kubernetes applications, try out some basic demo applications, run some simple applications, run through some of these sample commands, and that'll expose you to how pods work, how services work, network policy, and that as you get familiar, we'd like you to extend it to your community as well. You had a question?
Yeah.
Is it on?
Thank you.
Thank you.